the last lesson, we were taking a look at how to factor things and finding the greatest common factor. And then at the end, you might remember that we actually started factoring monomials. And that actually is the starting point for where we're going to think next, which is to try to actually factor polynomials. So we're not going to factor numbers anymore. We're going to sort of abstract that one level further and see if we take a polynomial, if we can factor it. It turns out we can, and there's some interesting techniques that we can develop that allow us to factor things pretty easily. I want to share some of them with you because it's sort of fun. All right, so let's just start off here by factoring this polynomial, 5x cubed minus 7x. Well, how would you factor that? Well, I look at this and I ask myself, is there any common factor? Meaning, is there any factor that both monomials have in common? I can ask what their greatest common factor is, and I see that the greatest common factor they have in common is just one factor of x. There's an x factor here and an x factor here. Oh, x factor. That's like a good name for it there. All right, so what would we have? What we'd have is that this would equal, if I factor out that x, what would I be left with? Well, here I'd be left with 5. Now, how many x's would I have? I have x times x times x right now. If I pulled one of them away, I'd just have x times x, which is x squared. Then I have to subtract off 7, and if I take away that x, if I factor it out, then it's no longer there, and I'm just left with minus 7. All right, is this really the right answer? Well, we can check this using the distributive property that we know holds. Remember, the distributive property says that if you have a times a quantity, b plus c, then that's the same thing as distributing the a to the b and the a to the c and seeing ab plus ac. So in fact, what we can do is we can just take this parentheses thing and take the a and make sure it hits everything with multiplication. If we do that, what would it look like? Well, it would look like taking this, putting it here, taking it, putting it here, and we take the product. What would we see? We'd see x times 5x squared, combining like terms, we see 5x cubed minus, and then 7 times x is going to be 7x, and we get the same answer. So in fact, this is the correct factorization. Let's try another example together. So the other example I want to look at is this fun one. 8 times a to the 5th minus 4a squared plus 20a. Let's see what the greatest thing we can factor out of this. Well, let's look at the coefficients first, these numbers in front, and notice that they actually all share what? What's their greatest common factor? I think it's 4. There's a factor of 4 here, a factor of 4 here, and a factor of 4 here, and that's the biggest thing to factor out. What about these a terms? Well, they each have at least one a, and that has exactly one a. So it sounds like 4a is the greatest common factor. When I factor that out, what happens? So now imagine I factor out 4 from the 8. That leaves me with a factor of 2. 4 times 2 is 8. And then here I have a times a times a times a times a. I take one of them away, so I have 4 a's left, which is a to the 4th power, minus, and then if I take away a 4, that's gone. Factor out the 4, that's gone. If I factor out one copy of my 2 a's, I'm left with just 1 a. And then finally, if I factor a 4 out of the 20, then I'm left with 5. 5 times 4 is 20. And the a I factored out already. And so I have this result. 4a times the quantity, 2a to the 4th minus a plus 5. And we can check that answer again by distributing. So if we distribute, I now have 3 terms. I would see this product, which would be 4 times 2 is 8. A times a to the 4th is a to the 5th, so there's that term, minus. And then I'd have a 4 times a times a, which is 4a squared, so that's good. And finally, I'd have a 4 times 5 is 20, 28 is checks. Let's try one last one together just for fun. Or maybe even another one. We'll see. If you ask me really nicely, I might do one extra one. We'll see. All right, what can we factor out of here? Well, I see negative 15w squared minus 10w cubed. First thing I notice is those negative signs sort of scare me. There's 2 negative signs. Let me actually factor out a negative sign. I can do that, it turns out. I can do anything I want as long as it's legal in the court of mathematics. I'm going to pull out a negative sign, and then I have a 15 and a 10. What's the greatest common factor there? Well, 5 is the biggest common factor. And I have w times w, and here I have w times w times w. w's can I pull out? Well, w squared. And when I do that, what am I left with? Now here it's a little bit tricky. I'm going to pull out a negative 5w squared. If I pull that out of here, what am I left with? Well, actually, just a 3. Now notice that that's a positive 3 because the 3 times the negative 5 will produce the negative 15 that you've earned. So here we have pulled out that negative sign in a way, and then plus, and then what do I have to multiply negative 5 by to make it equal to negative 10? Well, 2. 2 times negative 5 is negative 10. So notice the plus sign there too. So all the negative signs, all these subtraction thingies here have now been pulled off here to this negative, and now everything here is positive. And how many w's am I left with? Well, I had 3 of them. I pulled 2 of them away, so I'm left with 1. And again, you can check this and see that this is the correct factorization for this particular polynomial. Now, all right, you were good. I'll factor 1 more. Or at least we'll try. Here we go. 10n squared plus 3. All right, so let's look at the coefficients first. So the factors here are 2 and 5. The factors here are just 3. So they share no common factor, so that's not good. We can't factor anything out of there except for 1. And then here I have an n squared, but here I have no n's at all. So in fact, I can't even pull out an n. I can't pull out any numbers. Really, this polynomial can't be factored. So here's an example of a polynomial that can't be factored. Kind of fooled you. I said I'd do 1 more. It turns out I tried, but I couldn't. So here's an example of a polynomial that can't factor. All right. Well, now I'm going to show you my favorite factorization. I love it because it's A, easy, and B, follows us everywhere we go in every corner of mathematics. So it's something to really try to embrace. It's the difference of squares. Suppose that you have a squared minus b squared. Can you factor that? The answer is yes, and you can always factor it in the following really simple way. It's just the product of a plus b with a minus b. So a plus b times a minus b. Always, when you FOIL that out, you're going to get a squared plus b squared. Why? A times a squared. The outer terms produce a negative ab, and the inner terms produce a positive ab. So they actually cancel to give 0, and I'm left with b times negative b, which is negative b squared. There you have it. So now, armed with that, you can do all sorts of wacky, zany, crazy things. And what I want to know is, for each of these, do we in fact have a difference of 2 perfect squares? Let's look at the first one. Is that a difference of 2 perfect squares? The answer is absolutely. X squared is a perfect square. 100 is a perfect square. So I can instantly factor this as x plus 10 times x minus 10. I love it. Let's try another one. See if I can make it a little bit harder for you. 4w squared minus 9z to the 4th. Difference of 2 perfect squares? Yeah, actually yes. Because in fact, this is actually 2w all squared, and this is actually 3z squared all squared. You see? So here we can actually factor this as 2w plus 9z squared times 2w minus 9z squared. And if you FOIL that out, oh, typo. Why did you catch the typo? It's supposed to be 3. There we go. Because if you would check that, you would have seen that I was wrong. In fact, it's supposed to be 3, because that is 3z squared all squared. If you take 3z squared and you square it, you actually produce 9z to the 4th, which is what we want. So there we have it. Now it's correct. That's good. It's always good to find your own mistakes. And you can actually FOIL this out and see that we're going to get 4w squared minus 9z to the 4th. The z squared times z squared gives us the z to the 4th. All right, one final one. One more. Is this the difference of 2 perfect squares? Well, w to the 6th is a perfect square. It's w cubed squared. So that's good. And that's a difference, so that's good. Z to the 4th is a perfect square. It's z squared squared. But what about 8? 8 is not a perfect square. There's no whole number that when I square it, I actually produce 8. So in fact, this is not a difference of two perfect squares, and so I can't just easily use this difference of squares formula. In fact, I'll just leave it like that. Anyway, when you have the difference of two perfect squares, it turns out there's lots of structure and a really quick factorization. I'll see you soon. Let's try to factor using some other techniques. And why would you possibly want to use another technique? Well, let's take a look. Here's a really complicated polynomial. 8x cubed minus 20x squared plus 6x minus 15. Well, let's try to factor it using the old-fashioned things that we've developed so far. Do we have a common factor in every single term? Is there a factor they all share? Nothing beyond 1. And so, in fact, I can't even get off the ground by trying to factor out a common factor, because the only common factor we have is 1. That doesn't help us. Well, that's sad. So I look at this, and I ask myself, do I see any kind of coincidences within this? I can't be maybe greedy and ask for the whole thing to factor, but maybe I could be a little bit more modest, be a little bit nice and kinder and gentler. If I am a little bit modest, I'll notice something. These two terms have some common factors, right? In fact, they both share a factor, a coefficient of 4. 8 and 20, the greatest common factor is 4. And here I have x times x times x. Here I have x times x. So there's an x squared common factor as well. And so, in fact, what I can do is write this as factoring this piece. 4x squared times, and what's left over? Here I'm left with a 2x minus 5. And you can check that by distributing and seeing the 8x cubed minus 20x squared. But I still have this stuff here, so that's sort of sad. But maybe I can factor that a little bit. Is there a common factor? Well, sure, because in fact 3 is a common factor. If I factor out 3, what am I left with? Here I'm left with a 2x minus 5. Oh, wait a minute. It can't be true. It can't be true. Look at this. Now I've got 2x minus 5 as a common factor of the stuff I have now. This is unbelievable, isn't it? This is like magic. It's like a magic trick. You should show this to all your family tonight. Say, look at the magic trick. And now I can factor out 2x minus 5. And what am I left with? 4x squared plus 3. I have just factored this thing, which looks completely infactorable. And had I do it, I did it by taking a look at this group and factoring it, taking a look at this group and factoring it. And notice that the magic of math allowed me to discover that in this case, this was a common factor. This technique of taking this and grouping them and factoring this, grouping these and factoring this, is actually called factorization or factoring by grouping. Let's take a look at another example because it's just too good to be true. When this happens, by the way, I think it's just great. It's like a cosmic coincidence. I love it. I love it. Take a look at this. Let's see if we can factor this cubic. Is there a common factor I can pull out of everything? Plainly not, because here's 21, a 15, a 7, a 5. There are no x's here, so this is not good. Is there a cosmic coincidence? Let's take a look at these two. And notice that there's a common factor here. The numbers 21, 15, their greatest common factor is a 3. And I have an x cubed here and an x squared here, so we can pull out an x squared. And then what am I left with? When I factor that out, what times 3 gives me 21? That's 7. What times x squared gives me x cubed? That's x. Plus, and then here I'd have just 5, because 5 times 3x squared gives me a 15x squared. Plus, and then the rest, which can't be factored anymore. But hold on. If I put parentheses around there, look what I get. Another cosmic coincidence. 7x plus 5, 7x plus 5, I can factor that out of the whole thing. I love math. What am I left with? I'm left with 3x squared. And what am I left with here? Again, that's the invisible 1. There's an invisible 1 factor, so it's not 0, it's actually 1. So when we distribute, we actually get that term. And there you see the factorization of this complicated-looking cubic brought down to earth by just factoring by grouping.